Thank you, Sydney, for your presentation. Thank you for inviting us to present you what we are doing here in our company. And this is a concrete application where HPC is a need. We need it to develop this kind of algorithms. And please let me introduce QUIBIM. QUIBIM is a spin-off from La Fe Polytechnics and University Hospital here in Valencia. And what we are trying to do in the last years is going from a qualitative radiological report, which is based mainly on the direct observation of the medical images, to a quantitative one thanks to AI and automated analysis. So I'm sure that you all have seen these kind of images. Some years ago, when we went to the doctor to see the last scan that were performed to us, we saw these 2D images which were printed. However, and we can see we have very low spatial resolution. That means that when we are fixing on a concrete region from the images, we have components from different tissues. That's it. For example, if we see, see this region, we have components from the lung, from the heart, from the bone, or even from the skin. So if we want to analyze the lung, we are biased by the other components. So in the last years, a lot of investment and research have been done to digitalize these medical images. So thanks to digitalization, the medical imaging is one of the medical sectors that has experienced the higher technological revolution. So, however, this digitalization not only allows us to increase this spatial resolution, we can't forget that behind these pictures we have numbers. And these numbers are directly related with the biological processes that is happening on our bodies. So if we work with these numbers in the correct way, if we exploit them, we can go from a qualitative diagnosis to a quantitative one, and we can measure which is the grade of disease or health we have on our body. We are used to think that we can see everything with our eyes. However, when we are speaking about disease, we are speaking about small changes that are happening on the bodies. So we need to go deeper than the human eye to detect these diseases on the earlier stages. If we go back on time to 1896, we find the first radiological report, when we can find expression that there is no stone of appreciable size in the kidney, which is a qualitative diagnosis. However, if we go to a report from 2018, this year, in spite of the high amount of advances that the radiology has suffered, we find also radiological reports based on this free text. So we still find these qualitative reports even of the advances that the technology has suffered in the last year. And we find expressions like observe, seen, appreciate. However, what happened with these things that we can see? Where are they? They are a serious problem that maybe puts in danger the life of our patients. We can't know it just like viewing directly the images. We need to calculate, to extract quantitative data from these images. So we can think that all these images belong to healthy patients. However, so the diagnosis could be based on expression like there are not observed alterations, but if we observe them, we can't see how much alterations there are on these images. However, if we quantify them, if we extract quantitative data from them, we can see that behind all of them, we have a disease. We have a pathology. For example, on the first time image, after calculating the fat within the liver, we found that we have a high liver concentration, could be inferred or could progress to cirrhosis. Or in the second case, when we measured the volumes of the different regions from the brain, we found that we were behind a patient with Alzheimer's. So we found the main need of the radiological department, which is the need to measure. Lord Kelvin, known physicist, mathematician and engineer, once said that when you can measure what you are speaking about and express it in numbers, you know something about it. So there were a lot of truth behind his words. And from this need of measuring is when we obtain the concept of imaging biomarker. This is the definition, the correct definition of imaging biomarker, but it's a number which is directly related with a physiological or pathological process that is happening on a human being. And they can be extracted from the images by using computational models and artificial intelligence. This is the pipeline that we designed to develop these imaging biomarkers, going from the idea and the clinical need, which is very important. We need to have a clinical need to develop these algorithms, and to finally end on the clinical value. We need this clinical value also. In two of the steps of this pipeline, which are the image processing and the images analysis, is where AI are directly applied. Depending on the region that we want to analyze, the images that we have, we can extract different imaging biomarkers. For example, we can quantify the diffusion and the perfusion of a concrete tissue in order to assess an oncological process. Or for example, we can quantify the characteristics, the morphological and the mechanical characteristics using a computed tomography image to quantify, to assess an osteoporotic process. So depending which is the goal, which is the disease we want to treat, we apply different analysis, different analysis methods, and we use different images, going from magnetic resonance, computed tomography, X-rays. But a question that all of you are wondering is, why do we need HPC? Well, this question is easily answered knowing which are the challenges that we have to face when we are dealing with medical images. The first challenge that we have to face is that when we deal with medical images, due to the high spatial resolution that they have, we are dealing with images of high dimensionality. For example, when we are working with an X-ray, we have a 2D image, but the matrix size that each X-ray image is about 3,000 per 3,000 pixels. And when we go to a 3D image like computed tomography or MRI, we are dealing with more than 100 pixels per dimension. So with each image, we are working with millions of pixels. So we need a lot of memory to deal with these images. Directly directed with the previous challenge, and with the complexity that of the problems that we have to solve on the radiology sector, we are dealing with complex AI architectures, and concretely with complex CNN architectures. So, for example, in this case, we develop an algorithm to automatically segment a concrete region of the image. And we have to fix millions of parameters and deal with images that were generated through the different layers of the CNN in order to develop this model. Okay. And finally, the high computational cost that the mathematical models for extracting these imaging biomarkers, the requirement of the computational cost is very high, because we have to adapt, we have to extract, we use very complex mathematical models to extract these imaging biomarkers. So we need HPC integrated in healthcare and medical image in order to extract these imaging biomarkers as fast as possible without hindering to radiological workflow, because we can't avoid radiologists when go to diagnose a concrete image. We can do him to wait until we have this analysis performed. And which HPC installation does fit the best in the healthcare sector? Well, we can go from a local solution to a cloud-based one. However, if we want to install a local solution on each hospital that we want to install our software, it's very complex, especially on those clinics that are very small. So we deal with two different environments. To develop and to train our own models, our algorithms, we have a local solution. We have our own cluster. However, when we go to production, we have a cloud-based solution where the users or the radiologists, the researchers upload the images, they are anonymized and they are processed, and the images biomarkers are extracted on the cloud. And now we are going to see some applications that we have developed based on AI on our group in order to face three different problems that are nowadays on radiology, which are image segmentation, region detection, and image classification. And they are all related with a clinical need. The first clinical need is when we are dealing with diseases like cirrhosis, fibrosis on the liver. On these diseases, we need to quantify the fat and the iron within this organ. And nowadays, the gold standard is liver biopsy, which is an invasive technique, which is biased because we are only taking one small sample from the liver, and that is biased depending on who is doing this biopsy. Moreover, it difficults the patient follow-up because we can't doing the biopsy as many things as we want to the patient. So the solution that we propose is a virtual biopsy using magnetic resonance, which is obtaining from the images, pixel by pixel, the fat and the iron within the body. However, to do this analysis only on the liver, we need to segment it, to delineate where on the image the liver is. This is a time-consuming, exacting, and not rewarding task that requires radiologist expert knowledge, and therefore it is expensive in both time and costs. So the solution that we propose is the automatic liver segmentation through AI and CNS. So once we have our image, and by using the CNN, we can segment the liver organ, and we can automatically calculate, we can automatically quantify the fat fraction and the iron concentration on this organ, and we can know on each pixel from the liver which is this concentration, which is also important because now we know the concentration on each region from the liver and not only on a small region where the biopsy is taken, the sample is taken. Here we are going to see the advantages of using this automatic segmentation. On the left we have the segmentation by our AI tool, and on the right we have the segmentation by an experienced radiologist. The first one took only 3 seconds to do the segmentation, while the second one took 3 minutes, with the inconvenience that it hindered the radiologist workflow. So it's very important to make these tools in order to accelerate this diagnosis, this analysis. Now we are going to see another problem, which is the detection of the vertebra on an image, where each vertebra is. Because the vertebra localization and identification are essential for the diagnosis, the surgical planning, and the patient follow-up on spine pathologies. Nowadays, this identification is done manually, hindering radiologist workflow. So the solution that we propose is the automatic vertebra detection through AI. So having a CT image with arbitrary field of view, that means that it doesn't, it's not important which vertebra, how many vertebrae are visible on the image. We can detect and identify them by using artificial intelligence. Moreover, knowing where a concrete vertebra is, we can extract morphological characteristics from this region to assess osteoporotic processes. However, we can not only do detection to detect anatomical regions. We can only do detection to detect where the pathology is, where the disease is. It's the case of the pneumonia. The pneumonia accounts for over 15% of all deaths of children under 5 years old internationally. And the diagnosis of this pathology on chest X-ray is difficult because there are all another conditions in the lungs happening apart from this pneumonia. So the solution that we propose is the detection of this pneumonia to improve efficiency and reach of diagnosis services. In this case, we train a convolutional neural network by using a huge amount of level chest X-ray by experienced radiologists, and what we obtain is a model that allows us to detect the position of the pneumonia on a chest X-ray. And finally, I'm going to tell you about a concrete application on image classification that we have developed. It is based on the classification of a chest X-ray into normal or abnormal, depending if there is pathology or not, is not pathology present on this image. X-ray is the most performed examination. However, on radiological departments have limitations in reporting all these chest X-rays due to the limited resources available. So when you go to a radiology department, you can see huge amounts of papers that the radiologists need to inform. So what we need, the solution that we thought is that is to generate a classifier to automatically classify chest X-ray to prioritize those with abnormal findings. So what we will develop is having a chest X-ray, we train different classifiers to detect different pathologies. So we train different classifiers depending on the pathology, and the output of these, all of these classifiers was used to train another one in order to generate an abnormality score. And finally, I'm going to introduce you a concept that is nowadays on the radiology, which is radiomics. I think that all of you have heard about genomics, proteomics, and all these kind of sciences. And nowadays, thanks to the huge amount of imaging biomarkers that are extracted from these images, we can speak about radiomics. Radiomics is a multivariate analysis of large datasets of image biomarkers with the goal of finding diagnostic, prognostic, and therapeutic relations. That is, we have a dataset with lots of imaging biomarkers that are referred to a concrete pathology. So having these imaging biomarkers and the clinical variables, that is, for example, relapse, death, cure, we can establish correlations between all these variables in order to make prognostic and diagnostic models. So by the analysis of large amounts of population, we can do predictions on a concrete patient. So we will give a lot of diagnostic, prognostic, and therapeutic value to the healthcare. So the idea that I want you to give you to home is that powerful GPUs are a must to develop AI because of the high parallel computing requirements. As I have said before, we need to perform this kind of calculation, extraction of imaging biomarkers as fast as possible because we can hinder radiologists' workflow. We need that every day when our radiologists go to inform a concrete image to have these parameters extracted. And we can't do the radiologists, we can always wait until this analysis finishes. And of course, it could be done with a multidisciplinary group that I read a lot. And of course, thanks to AI, we can go deeper than our human eye. So thank you. And if you have any questions.
How big are the learning data sets? How many images on average?
For classification and for detection, we need for the chest X-ray classification, nowadays we are working with 4,000 scans, and it doesn't work as good as we want with this dataset. So we need, I think, maybe 1 million images to classification. On the other hand, for segmentation, they are not needed too much images. For example, this liver segmentation is done using just 100 images, manually labeled. That's because we are working with 3D images. So each image from this, the radiological images are 3D, so you have different slices from the body, so you can use the different slices to train the model.
Okay.
So with just 100 studies, we are now about 98% of accuracy.
How many GPUs are you using?
Sorry?
How many GPUs?
GPUs? We have on the group what we have is a cluster to train, which is to train them. We use a cluster with 2 nodes, and each node with 2 GPUs.
I would have thought it'd be bigger.
Yeah, we know it. It's what we have nowadays.
If you had access to a cluster that was hundreds of thousand times bigger, what could you do with it?
How?
If you had access to a cluster that was 100,000 times bigger, what could you do with it?
What
What could you do? Would you be able to take advantage of having access to a cluster 100,000 times bigger?
Because we can do analysis, different analysis, because nowadays we can launch at the same time maybe 10 analyses, so we could launch lots of them, having a higher, and also on time.
How about on learning? How about on the deep learning?
The time?
The learning, the training of the algorithms
With
a bigger cluster.
well, in just some minutes. Now it takes us with this maybe some hours, maybe 8 hours or so. So with a bigger one,
With a small data set, and you want the data set to be much bigger. So
Yeah. Nowadays, for the pneumonia, maybe we can be 5 days training just one test. So yeah, to develop them will be faster, having lots of GPUs.
Are you using CUDA or OpenCL?
Yeah, CUDA.
CUDA.
And what is the AI framework? You know?
Yeah, we are using TensorFlow.
Very cool. Yeah.
Thank you.
Have you tried any multifractal analysis on different structures? I know that for tumors,
Yeah,
it's well known that there is a change
exactly.
which is crucial for treatment.
Yeah.
But
Yeah, fractal is used mainly to know the vessels, how have changed on an oncological process. And also, I don't know really, but I think that on bone is used also to know the morphology of the bone. Questions? So thank you.